On July 2, 2025, NASA's Fermi Gamma-ray Space Telescope did something it almost never does. It issued an alert, then it issued another, and another. For 3 hours, Fermi's detectors recorded numerous separate high-energy radiation bursts coming from the same point in the sky. By the time the signal finally faded, more than 7 hours had passed. In the entire recorded history of gamma-ray burst astronomy, over 15,000 events detected over roughly 50 years, nothing had ever lasted this long. GRB 20702b is not the longest gamma-ray burst ever observed. It lasted nearly twice as long as the previous record, and no one fully understands why. To understand why this event is so unusual, it helps to understand what a gamma-ray burst normally looks like. These are among the most energetic events in the universe, and rank second only to the Big Bang in terms of raw power. They typically occur when catastrophic processes, such as the collapse of a massive star or the merger of two neutron stars, create a new black hole. Part of the falling matter is directed into jets that shoot outward at nearly the speed of light, producing gamma rays so intense they can be detected billions of light years away. Most bursts end within seconds. In the standard classification, a long burst lasts a few minutes. An event lasting longer than a few hours should not exist in any standard model. GRB 20702b not only exceeded the expected limits, it completely obliterated them. Of the approximately 15,000 bursts cataloged since this phenomenon was first noticed in 1973, only half a dozen come close to this duration, and none of them match the peculiar behavior of this event, which not only slowly faded but produced 3 separate distinct pulses over its 7-hour duration. This repetition is significant. Gamma-ray bursts are, by definition, catastrophic. They typically destroy the physical process that produces them in a single irreversible event. A burst that fires, pauses, fires again, and fires again indicates something fundamentally different, something that persists over and over for hours. Detection required something beyond a single instrument. Fermi's gamma-ray burst monitor initially caught the signal, but reached its observational limits due to the event's length. NASA's Burst Alert Telescope at the Neil Gehrels Swift Observatory also detected it. The Russian CONUS instrument on NASA's WIN spacecraft recorded the event as well. The gamma-ray spectrometer on the Psyche spacecraft, currently en route to an asteroid in the main belt, did the same. The Japanese MAXI instrument on the International Space Station also provided data. Astrophysicist Eric Burns from Louisiana State University, who participated in the analysis, stated it plainly. The explosion lasted so long that no single high-energy monitor in space had the capability to observe it in its entirety. Researchers were only able to reconstruct the full picture by combining data from multiple spacecraft simultaneously. Its location added to the complexity. The source was located in the direction of the Scutum constellation, near the dense, dust-filled midplane of the Milky Way. Initial observations could not confirm whether the event was local, somewhere within our own galaxy, or truly extragalactic. This question was resolved by infrared observations from ESO's Very Large Telescope, which detected a faint increase in light emission consistent with a distant source. Observations made on October 5, 2025, with the James Webb Space Telescope provided the clearest image of the host galaxy, a massive, dust-shrouded system whose light has been traveling toward us for approximately 8 billion years. We are witnessing an explosion that occurred when the universe was less than 6 billion years old. The host galaxy is also extraordinary. More than twice the mass of the Milky Way, it is the largest and brightest galaxy ever found to host any type of gamma-ray burst. Webb also delivered an unexpected negative result. When a massive star collapses into a black hole and produces a gamma-ray burst, this event is usually accompanied by a supernova, a secondary optical brightening that occurs a few days to weeks after the burst. No supernova was detected in the afterglow of GRB 20702b. This absence does not rule out the star's collapse, as the massive dust column surrounding the source could have obscured any supernova emission. However, it removes the element that would otherwise most clearly confirm the origin of the standard long burst. Another factor complicating the situation is that China's Einstein Probe satellite detected X-ray emission from the same location exactly 1 day before the main burst began. NASA's X-ray telescope NuSTAR observed X-ray flares continuing for 2 days after the explosion ended. Neither the pre-explosion X-ray activity nor these post-explosion flares are typical of known gamma-ray burst mechanisms. The timeline of this event, the preceding X-rays, the 7-hour gamma-ray bursts, the subsequent X-ray flares, does not fit the fast, clean, and irreversible profile of a standard stellar collapse or neutron star merger. 3 main explanations are currently being investigated. The first is helium fusion. In a binary system, a massive star that has lost its outer hydrogen layers, a stripped helium star, and a stellar mass black hole spiral inward, eventually consuming its companion. As the black hole enters the star's interior, it draws in large amounts of material over a long period of time, creating a jet that lasts much longer than a standard collapse event. The second possibility is a tidal disruption event, where a medium-mass black hole, approximately several thousand times the mass of the Sun, shreds a star that passes too close to it. Tidal disruption events are known to produce long-term X-ray emission, and some have been associated with high-energy transient events, but a full gamma-ray burst of this nature has not been confirmed before. The third possibility is an unusual type of massive star collapse, such as a collapsed star in a hydrogen-stripped precursor, which manages to sustain a jet for much longer than typical collapses. None of these explanations fully account for all the observed features at once. The large, dusty host galaxy does not resemble the small, low metallicity galaxies where most stellar collapse explosions occur. The repeated oscillations do not fully align with a single tidal disruption event. The absence of a detected supernova leaves the collapse scenario incomplete. Researchers from George Washington University, North Carolina State University, Carnegie Mellon Louisiana State University, and Curtin University in Australia are among the teams working on competing analyses, and the data continue to be consistent with multiple models. Jonathan Carney, a graduate student at the University of North Carolina who led one of the observational studies, said this event will serve as a reference point. When future astronomers find similar explosions, they will ask whether these events match the characteristics of GRB 20702b or still represent something different. There is also a broader observational challenge in this discovery. Ultra-long gamma-ray bursts develop slowly and emit weaker emissions per unit time compared to the sharp peaks that automatic detection systems are optimized to capture. This suggests that the archive of detected bursts may be systematically incomplete, meaning other long-duration events may have been recorded but unrecognized, buried in data streams filtered for brevity. Detection strategies designed around standard burst timescales may miss an entire class of slower-developing phenomena. NASA's COSI mission Compton Spectrometer and Imager is scheduled for launch in 2027, with enhanced sensitivity to unusual gamma-ray transient events, including extremely long-duration ones. Whether GRB 20102b is a singular exception, or the first clearly documented example of a larger, systematically undetectable population, is a question that future observations and future instruments may answer. What is already clear is that this event does not fit into the framework that astronomy has used for 50 years to understand gamma-ray bursts. Something operated a relative jet engine for 7 hours, pulsed 3 times, and left an X-ray afterglow in one of the largest dust-filled galaxies associated with any type of explosion. The universe has done something here that current models, based on fundamental principles, cannot explain. This is not a failure of astronomy. It is an example of how the field progresses when an event occurs that forces all existing theories to account for something new,